Hello. Let me present my implementation of a queue and an application for the Minneapolis Institute of Art Museum documentation using the RAG, Retrieval-Augmented Generation, architecture. The presentation was prepared as part of the RS School AWS Practitioner course assignment. The app consists of a backend and a web interface. The entire app is built in JavaScript. The backend runs in Docker Compose and has 3 interconnected containers. A vector database, ChromaDB, latest version, using the HF embedding models, sentence transformers, all minimum L6v2. A separate, Envoy, container for authenticated access to the database via a static token. A REST API client, built with Nest.js, with 3 endpoints, status, search, and metrics. The app handles the full pipeline. Receiving a client request, then searching relevant documents in the vector database, then generating context, and querying the LLM. The LLM used is Google Gemma 29B model. Docker image sizes are kept minimal. For example, the main REST client image is only 300 megabytes on Windows, even smaller on Unix. This was achieved using Alpine Node.js version 23.5 and compiling the code into a single 3 megabytes file with sbuild, no extra dependencies needed. The app keeps detailed logs and statistics. Every request gets a unique ID for tracking. Logs are streamed, support levels 1.5, and include error logging with configurable rotation. There's also a request cache, currently a JSON file, and built-in analytics. Here's how the logs look. Here's the error log. Here's the cache. And here's the stats. To populate the vector database, I wrote a script that parses JSON docs from a folder, splits them into 750 token chunks with 100 token overlaps, feeds them into the database. Processing 100K plus files took hours, with only one read error, due to file access. The script can resume from where it stopped. The final database size was 613 megabytes. The backend handles search and generation in one pipeline. Request timeout after 25 seconds, returns a 500 for error if they do. The REST client has detailed Swagger docs. Here's how it works. First, let's check the server status. Everything is fine. The server provided a correct response. Now let's look at the statistics. The server gave a statistics response. And this is what the main request for information search looks like in Swagger. I won't show it now, it's better implemented in the web application. The web app is built in React. Let me show it in action. The main interface has a large input field and settings like number of vector results, token limit, question type for the LLM. This affects responses. For example, type 0 asks the LLM to answer literally, but it references the vector DB context, which isn't ideal since users can't see it. After testing, types 3 and 4 work best. You can compare the results yourself. Another useful feature is raw debug data, enabled by a toggle, which shows extra server info. Besides the LLM response, the app returns metadata, including relevant images and links, validated by the server first. Let me demo a few queries. I have selected several query options and now we will see what the results will be. Let's start by asking, what African artifacts are in the museum's collection? I used the default settings and should get the shortest answer. Now I will increase the number of vector results and the number of tokens. I will change the LLM question variant and set the query to be context-specific. We see that the model is context-specific and the answer is different. Now I will change the LLM question variant to 3. I should get the longest answer but without context reference. You've probably noticed that the server response isn't plain text, it comes formatted. That's because the context we get from the vector database is already structured, and the LLM keeps this formatting in its answers. I implemented special parsing to clean this up, which gave us nice readable results. The REST API also returns some metadata. We use this metadata to create the See Also section. The server finds relevant images from the collection and checks all links to make sure they work. You can click any of these links to learn more. So now we get well-formatted answers plus useful references that are guaranteed to work. It's all automated. The system checks everything before showing you the results. Now I will send a few more requests. Now you can see the statistics. This is how the application turned out. A little later I will try to make a better presentation and improve the application. For more details, check my repository, link in the video description. Thanks for watching.